The twinkling stars that adorn our night sky are more than just points of light. They are celestial objects, immense balls of burning gas that hold the key to understanding the universe. These stars, scattered across the vast expanse of space, are not all the same. They vary in size, temperature, color, and luminosity. One of the primary ways astronomers study and classify these stars is through their spectra. These spectra, akin to stellar fingerprints, reveal a wealth of information about a star's temperature, composition, and even its life cycle. Join us on a journey as we delve into the fascinating world of star classification and explore the diverse range of stellar objects that populate our cosmos. Astronomers categorize stars based on their spectra. A star's spectrum is created by splitting its light into its different wavelengths, much like a prism disperses sunlight into a rainbow. By analyzing the dark lines and bands, absorption lines, present in a star's spectrum, astronomers can identify the elements present in the star's atmosphere. This is because each element absorbs light at specific wavelengths, creating a unique spectral signature. Based on these spectral characteristics, astronomers have developed a classification system for stars known as spectral classes. The spectral classes are arranged in order of decreasing temperature, from the hottest to the coolest. Each spectral class is further subdivided into 10 subclasses, numbered from 0 to 9, with 0 being the hottest and 9 being the coolest. At the extreme end of the spectral classification system lie the Class O stars, the hottest and most massive stars in the universe. These stellar behemoths, with surface temperatures exceeding 30,000 Kelvin, shine with an intense blue-white light. Due to their immense mass, Class O stars have incredibly short lifespans, burning through their nuclear fuel at an astonishing rate. They live fast and die young, often ending their lives in spectacular supernova explosions. One of the most well-known examples of a Class O star is Zeta Puppis, also known as Naos. Located in the constellation Puppis, Zeta Puppis is a blue supergiant with a surface temperature of around 40,000 Kelvin. These stars are relatively rare, as their short lifespans mean that they represent a brief stage in a star's evolution. They are typically found in regions of active star formation, such as the spiral arms of galaxies. Following closely behind Class O stars are Class B and A stars, also hot and bright, but slightly cooler and less massive than their O-type counterparts. Class B stars, with surface temperatures ranging from 10,000 to 30,000 Kelvin, shine with a brilliant blue-white light. These stars are still incredibly luminous and massive, but they have longer lifespans than Class O stars. One of the most famous examples of a Class B star is Rigel, the brightest star in the constellation Orion. Rigel is a blue supergiant with a surface temperature of around 12,000 Kelvin. Class A stars, with surface temperatures ranging from 7,500 to 10,000 Kelvin, shine with a white or slightly blue-white light. These stars are more common than Class O and B stars and have even longer lifespans. Sirius, the brightest star in the night sky, is a Class A star with a surface temperature of around 9,900 Kelvin. Section 5, Class F and G, similar to our Sun. As we move down the spectral classification system, we encounter stars that are more similar to our Sun. Class F and G stars are intermediate mass stars with surface temperatures that are more conducive to supporting life. Class F stars, with surface temperatures ranging from 6,000 to 7,500 Kelvin, shine with a yellow-white light. These stars are slightly hotter and more massive than our Sun. Procyon, the brightest star in the constellation Canis Minor, is a Class F star with a surface temperature of around 6,600 Kelvin. Class G stars, like our Sun, have surface temperatures ranging from 5,200 to 6,000 Kelvin and shine with a yellow light. These stars are the most well-studied stars in the universe, as our Sun serves as the archetype for this spectral class. The Sun, a yellow dwarf star with a surface temperature of around 5,778 Kelvin, is the closest star to Earth. Section 6, Class K orange stars. Cooler than Class G stars are Class K stars, which have surface temperatures ranging from 3,700 to 5,200 Kelvin. These stars shine with an orange light and are slightly cooler and less massive than our Sun. Class K stars have longer lifespans than our Sun and are thought to be ideal candidates for hosting planets with life. This is because their habitable zones, the regions around a star where liquid water can exist on the surface of a planet, are wider and more stable than those of hotter stars. One of the most well-known examples of a Class K star is Arcturus, the brightest star in the constellation Bootes. Arcturus is an orange giant with a surface temperature of around 4,300 Kelvin. Section 7, Class M, red dwarf stars. At the bottom of the spectral classification system lie the Class M stars, the coolest and least massive stars in the universe. These stars, also known as red dwarfs, have surface temperatures below 3,700 Kelvin and shine with a faint red light. Despite their small size and low luminosity, Class M stars are the most common type of star in the Milky Way galaxy. They make up around 85% of the stars in our galaxy. Red dwarfs have incredibly long lifespans, much longer than the current age of the universe. This means that all of the red dwarfs that have ever formed are still shining today. One of the closest stars to Earth, Proxima Centauri, is a Class M star located just 4.24 light-years away. Section 8, Conclusion. Spectral classification is an essential tool in astronomy. It allows astronomers to organize and study the vast diversity of stars in the universe. By understanding the characteristics of different spectral types, we gain insights into the processes of stellar evolution, the formation of planetary systems, and the search for life beyond Earth. The study of spectral types has revealed a remarkable diversity in the properties of stars, from the blazing blue giants to the faint red dwarfs. Each spectral type represents a different stage in a star's life cycle, and by studying these stars, we can piece together the evolution of our own Sun and the countless other stars that populate the cosmos. As we continue to explore the universe and unravel its mysteries, spectral classification will remain an indispensable tool for astronomers.